Everybody, my name's Sawyer Rodriguez. I'm doing my project on Scorigami. For those of you who aren't familiar with the concept, it is the study of getting unique scores in American football. Specifically American football, because if you think about it, other sports, uh, the way that a score becomes unique or becomes interesting is kind of just in terms of magnitude or how much another team scores versus another, which with football, it's a little bit different. But for soccer, for example, 2-1 is a pretty common score. 3-1 is a pretty common score. You score in increments of one. So, a score just really isn't that unique or interesting because they pretty much happen all the time. These 2-1 games, 2-2 games, they're not really interesting. A game will catch your eye if someone wins a soccer game 10-1, but it's very rare and doesn't really yield any interesting results, especially in terms of number theory. But for football, it's a little bit different. The building blocks of scoring are not ones and twos and threes and fours. It's just twos for a safety. We have a 6-point touchdown, a 3-point field goal, and then a touchdown with a 2-point conversion, which is a total of 8 points, and then the standard touchdown with an extra point. I know if you don't watch football, maybe that was a lot of like word vomit, didn't make much sense. I'll break it down a little bit, but just for those of you who have a brief understanding of football, the increments of scoring are 2 points, 3 points, 7 points, 8 points. And that yields a lot of interesting results because, 3 of those 4 numbers are prime numbers. 2 is a prime number, 3 is a prime number, 7 is a prime number. So the addition of these kind of lend themselves to an interesting theorem, which we'll talk later, which we've talked about in class, that has to do and kind of ties the kind of more football, sporty side of it to the number theory. So here we can see that, I'll load it right here. Here is the Scorigami board. So before we kind of get into what Scorigami is, how you get it, I think it's important to understand what this graph looks like. So here we can see the Scorigami board where we have on the top part the team's winning score and on this side part here the losing score. So kind of an example of what a Scorigami is all these green dots or all these green blocks are scores that have happened before. So you can't tell the frequency, you can't tell anything. If it's green, that just means it's happened. So here, for example, we see this 73-0. 73-0 has happened, believe it or not. But all these values here, 67, 68, 69, 70-0, they haven't happened. And it's kind of interesting because, there's a lot of these clustered points here that are kind of, fragmented relative to this big old block here. But there's reasons why, and we'll kind of talk about that. But this is basically what the chart looks like, and if you can read this, you'll follow along pretty well. So an example of another Scorigami is, we obviously talked about this 72-0, or 73-0, excuse me. But then a score that hasn't happened yet is 32-11. Like we said, the scoring in football is a little bit different. It's 2s, 3s, 7s, 8s. So to get an 11, you'd have to score 8 points, which would require you to score a touchdown, a 2-point conversion, which is not very common, and then a field goal, which for all 3 of those things to happen is not the most common thing. Not to mention that you have another component where you have another team whose score also has to be kind of unique, where 32 is an even number and can be broken down into prime numbers as well. You realize when you break down these numbers that a lot of these open spaces of scores that haven't happened are prime numbers or are just very difficult to make with the building blocks we have with 3s, 7s, 8s, and 2s. So that is kind of where Scorigami is interesting, is because a lot of these scores, they aren't very common to get, but all the ones around them are filled. This, for example, is this little block here hasn't been filled, but every single block around it has been, which is it's really interesting just to see that, because then you have pockets here where it's more common to not have Scorigami. But here we can see the frequency of scores that have happened in the NFL. So like we said in soccer, very common scores are 2s, 1s, 1-2 is a very common score. The NFL equivalent of like a 2-1 score in soccer is a 20-17, which has happened 286 times. Super common score. And the reason why is because when you break it down, 17 is just 2 touchdowns and a field goal. And those are really common to get in an NFL game. And then 20 is kind of the same deal. It's 2 touchdowns, 2 field goals. And that's just kind of how these games happen where, it just ends up being a really common score. Here, for example, we see a 33 to, you can't see it here, but it's 33 to 15, which when you break 33 down, you break that into 3 prime numbers. You break it down to 11, and 11, which independently getting 11 one time is difficult. To get it twice is hard. To get 3 times is nearly impossible. So just to that end, that's why this score is not very common, but here it is a Scorigami. Now, we see this in this slide, kind of what contributes to a Scorigami. There's about 3 things that I think are really important to establishing a Scorigami. The first is lopsided scoring. So lopsided scoring is basically what we saw in our first example, the 73-0 score. It's happened once. It probably won't happen again. If you shut out a team in an NFL game, it's super uncommon. To do that and then to score a bunch of points is pretty much impossible. We'll probably never see a Scorigami like that ever again. Another way is through just 2 teams scoring a lot of points. So for example, here we have 43-33, which, it's just in terms of magnitude, you have 2 teams that are scoring way above average in terms of points. It lends itself to being a unique score. And so we can see that up here. Here is kind of the shutout victories where the winning team scores a ridiculously high amount of points here, and the losing team doesn't really break past 20 points. So this is kind of that lopsided margin. Right here is like the lopsided margin where, one team scores a bunch of points, one team gets shut out. It lends itself to Scorigami. Here is the pocket of where both teams score a lot of points. So we have like 50. Let's see, we got about 58 to 37 or 36. It's just a really unique score just in terms of magnitude from the winning team side and in terms of primality between both those scores. To make those numbers up with the building blocks of 2s, 3s, 7s, and 8s it's difficult. We'll get more towards the number 30 side of it in a second, but just so you get the general idea of what Scorigami is, how you can get it, that's kind of where it comes into play. And so now the third way to get Scorigami is kind of what we talked about here. These little pockets right here, where it takes a unique combination of those point values to yield these scores. Because these scores aren't like super, like for example, 22 is not a super high scoring game in terms of the NFL, and then 11 is also not a very high scoring game. Those scores are difficult to get just because when you split them up, you realize that they're made of prime numbers, and then through the building blocks of the NFL, it's just difficult to get those. So we'll explain that further, percentages and everything here in a little bit, but that's basically how you get a Scorigami. So here we can see point values and their frequency. So like we said, a touchdown is 7 points. A touchdown plus a PAT, is 7 points. A touchdown in and of itself is 6 points. That's not really interesting because we have field goals, which a touchdown, if it's just 6 points, is just basically 2 field goals, which happens. But we see this touchdown, these 7 points, in the 2016-2017 NFL season. We scored 1,146 touchdowns, which per drive, 17.2% of drives, NFL drives, led to a touchdown. Here we can kind of see these percentages decrease as the scores, or as we get different scores. So for example, a field goal happened on 10% of drives, and the touchdown plus a 2-point conversion right here happened 45 times that season, which basically only happened in 1 out of every 100 drives. So that's just really unique in and of itself. And then the golden gem, I think, of Scorigami, which really kind of throws a wrench in this whole thing, is this 2-point safety, which doesn't happen very often, but when it does, you can kind of put this team or put that game on Scorigami watch, just because the rarity of this combined with the frequency of the 7s kind of yield interesting results. So, for example, if we had a field goal and a 2-point conversion, that yields 5 points, which is just a very difficult score to get in the NFL. And I'll plot that later so you can see. But basically, that's kind of where this stems from. So we talked about building blocks. So we have these scores right here. And this is taken from John Boyce, who created Scorigami. This is taken from kind of his presentation, just because I think there's not really a better way to describe it, which is like using these points as building blocks. So if you wanted to score 8 points in an NFL game, you could do that by scoring a touchdown and a 2-point conversion, which is the most likely way. 2 field goals and a safety, and then we get down to this 4 safeties, which we talked about here. Is very uncommon to get 4 safeties in a game. To get 8 points it's probably never going to happen, honestly. But basically, this is kind of shows you how difficult it is to get certain point values depending on the building blocks you use to achieve them. So this 8-point value, 8 is not like a super high scoring thing. I mean, 8 is, I would say, pretty common, but to do it doing a 6-point touchdown and a safety is 4,000, basically 4,500 to 1 odds to do that. It's just very rare. So whenever you get these really high scoring games that are multiples of 8, it yields really interesting results. So feel free to read this. I'm not going to go through that because we kind of already talked about it. So how this relates to number theory is actually, I think, really important. What made me think of this as kind of a subject to talk about was we were talking about Goldbach's conjecture one day in class, and I already knew that there were some scores in the NFL that are just difficult to get, and this kind of made sense why. So this is important for 2 reasons. The first is because it helped me realize this could be a project to do. Second is because it helped me develop a code that was able to break down most likely Scorigamis and all that kind of stuff. So I'll increment that, or I'll show you that later in this presentation, but this is basically the backbone of why I thought this was important. So basically what Goldbach's conjecture states is that every even number can be the sum of 2 prime numbers. And Goldbach's weak conjecture is every odd number can be broken into 3 prime numbers. So that kind of made sense when I thought about it, because some of the most difficult scores to get in the NFL are 22, 33. These numbers. So 22, for example, you would have to get 11 twice. It's broken down into 2 prime numbers. 11 is a prime number. 11 is difficult to get in the NFL, as we can see here. 11 points. To get only 11 points in a game, you have a 0.15% chance to do that. And that's the most likely scenario, where you have a 2-point conversion here and a field goal, which would yield 11 points. Least likely, this is kind of just more of a brain game. You have 3 field goals and a 2-point conversion. It leaves you with, practically no chance to get 11 points. But, you relate that over to this side, where you have 17 points, which you talked about earlier, is a very common value. That can be 0.3%. So you definitely can, when comparing these 2 values between 17 points and 11 points, you see that it's definitely easier to get 17 than it is to get 11. And so that's why Scorigami is so important, and that's why Goldbach's conjecture kind of really helps formulate this idea that some scores are harder to get, because when you break them down into the sum of prime numbers, you realize those prime numbers are hard to get with the building blocks that are built around football, which is, like I said, 2s, 3s, 7s, and 8s. So you see these are the most likely and least likely permutations to develop these values. So like I said, I coded something, and this is kind of everything else up to this point was more just so you can kind of get a background. This is more my project, which was basically finding trends having to do with Scorigami. So what I first did was I wrote a code that was able to figure out of all the scores that were left in Scorigami, all the scores that have still not happened yet, is there anything to be said about even or odd? Because like we said, Goldbach's conjecture stated that even numbers can be divided into the sum of 2 prime numbers, and then odd numbers could be the sum of 3 prime numbers. So I wanted to see if there was anything having to do with that in our Scorigami board. So there really kind of wasn't what I thought would be the issue. Even scores were actually a lot harder to come by in the NFL. I figured if you could break them down to the sum of two prime numbers, it would be easier to get, thus leading to less places on the board where you have even scores. But that wasn't the case. Actually, even was the hardest to come by in the NFL. Here you can kind of go through, and we'll talk about this later. But basically, we found that even scores were the most common, or the least common, excuse me, and then odd scores were the least, or the most common, excuse me, in these NFL games, which I thought was really interesting because I thought it would be kind of an even split all across the board. So here's kind of the code. I'm not sure if people are interested in this, but this is what I used to figure out the whether a score was even or even odd. I went through and found a spreadsheet of all of the scores that have still not happened yet, and incremented through. Use a modulus 2 to figure out which one was even, which was an odd, and then counted it all. And so here's basically what we said. Even scores were the least common. Odd even scores were kind of middle most common. And then the odd to odd final scores were the most common, which I thought that was a little bit interesting. So now what I did is I went through and figured out each different permutation that was required to get, specific point values. So for example, to score 2 points, there's only one permutation to do that, and that's just to score a 2-point conversion. To score 7 points, kind of the same deal, more or less. You can do it scoring 7 points. You can do it scoring a 2-point conversion, a field goal, and another 2-point conversion. You basically, the larger the number, the more permutations are required to make that number. So basically what I went through is I went through 1 to 73, because 73 is the most points scored in a game, and broke it down by the amount of permutations and the most likely permutations associated with the percentage associated to that point value. Kind of a mouthful, but I think you'll see what I mean here in a second. Like I said, for those interested, this is the code that I used. Here were the given point values, these given scores, and then these probabilities were the probabilities talked about in one of the previous slides, where 0.172 was the probability for a touchdown, all the way down to 0.006, which was the probability of a 2-point conversion. So we went through here, and then this was kind of the list that I had formulated. There's 17% chance to end the game as just scoring a touchdown. And then as you go down, the scores become less and less common. So they're organized by decreasing order of likelihood based off of the percentages associated with the permutations that build these numbers. So our numbers up here really aren't that interesting. They're kind of our standard building blocks. But what I thought was really interesting is that, for example, it's easier to score 28 points in a game than it is to score 5 points, which I think is just kind of a weird thing. And you go down here, it's easier to score. It's almost as easy to score 42 points as it is to score two safeties, which, you kind of see these values here. They're not really that intriguing. But as you go down, you kind of get this weird run of numbers where you've got 18, 16, 35, 12, 31, 29. It's almost like there's no rhyme or reason as to, why these numbers are more likely to get scored or less likely to get scored. So I thought it was really interesting just to see how breaking up these prime numbers contributed to the likelihood of these points being scored in an NFL game. So this is the winning scores. So like we said, there's winning scores and losing scores. These were the winning scores. The losing scores was also interesting because, you kind of get a similar run of numbers where, you got this 21, 17, 15, 13, 11. But then, you kind of throw a wrench in it here where, you got like 35, 12, 31, 29. It's just a very interesting, weird kind of thing. And also with the losing scores, no one wins a game scoring 0 points. So that's why 0 didn't show up in this graph here. But here we see 0 to get shut out in an NFL game. There's a 0.02% chance that happens. So that's just another thing to think about here. But I definitely think that this yields really interesting results, especially when we see most likely Scorigamis to be broken. So basically, the code for that was this, where we did our combined probabilities, where we incremented through the total amount of Scorigamis left on our board, basically multiply the percentages together to get the likelihood of specific values to be broken. So this is kind of the moment of truth, and this was kind of what a lot of my code was predicated on finding, was this, which basically shows the most likely Scorigamis to be broken. These are all Scorigamis that are still left on our board, and this is the likelihood that they will be broken based off the algorithm that I wrote. I think this is really cool, and this is the last slide on the presentation. I thought this was really cool because the original video that John Boyce did, it was more basically talking about the idea, the concept of Scorigami, but there wasn't really a lot of percentages or any algorithms or any studies that were done on what Scorigami might be broken next, or and he didn't really talk about prime numbers or anything like that. So I feel like that's kind of where I feel like this presentation would be good and kind of an interesting study, because you kind of look online, like, is there a Scorigami that's most likely to be broken or whatever? No one had an answer. So I figured, it would be kind of cool to go through and develop a code that would basically take into account prime numbers, take into account Goldbach's conjecture as basically as a jumping off point to figure out different permutations that equal these point values in football games, and then develop a percentage associated with that, given these final scores. So I could talk about this for a while. I'll briefly show the code that I wrote to write all this. I kind of just snippets throughout the presentation, but just if anyone's interested, this is what I used, and I did this all in RStudio to be able to formulate these percentages. A lot of these codes are kind of repeats because I was having some difficult times figuring out what exactly was going wrong, because I was getting some weird percentages in some of them. But yeah, so basically this is, the presentation. I'll go through real quick and kind of just show some interesting scores that I think are likely to be broken. Like this 29-8. Scoring is pretty frequent in the NFL, and if I were to redo this code again, I'd probably take that into account, because scoring a low amount of points in the game is not super common. But then it's this kind of pocket of scores that I think would be possible, like this 22-11, I think is plausible given the current state of the NFL. These numbers are basically just raw values where you're basically just plugging and chugging the percentages of sevens, threes, and all that. But it doesn't take into account the flow of the game. It doesn't take into account how the NFL today is higher scoring than it was years and years ago. So this pocket right here is probably the most interesting because it yields results like 25-8, 22-11, 20-11, 18-11, 18-9. These scores are you could see them happening if you watch football. You can kind of see that the way the game is played today, those scores are probably more likely. So this is not an exhaustive list. Obviously, there's more, but as you get down, the likelihood of them just goes way low. But here, like I said, is the final product and kind of what is the magnum opus of this project. It took a sizable amount of time and a lot of coding, a lot of coffee to be able to compute this. But yeah, so I definitely think that this kind of ties together what we learned in number theory with Goldbach's conjecture, kind of the interesting properties of prime numbers and how adding them together yields very unique values, and in this case unique patterns, and then being able to basically plot percentages when no one had done that, I thought was a pretty cool thing, and gave me a really cool excuse to dive deep into something that I've always thought was interesting and whatever. So I'll link the code in this video if anyone is interested in that. I'll link this presentation as well. But thank you for watching, and I hope you learned a little bit about number theory, a little bit about prime numbers. And if you're watching a football game in the near future, whatever, you have this in the back of your mind. If you want to make a small conversation with somebody, you could be like, hey, Scorigami, you ever heard of it? And maybe you can pull out this video and just let them watch the whole thing. Just kidding. But that's basically the project. So thank you so much for watching. And Dr. Banks, if you're watching this, thank you for teaching a great class this semester. I really appreciated a lot of the time and effort you put into it. So thank you. And I hope everyone has a great winter break.